Hello everyone, I welcome you all to this class. This is a mathematics class. We are here again to consider this important topic, the Rolle's theorem. So we are going to start the class by stating what this theorem says. Now suppose you have a function which is suppose you have a function f which is continuous on a closed and bounded interval a comma b, and that function is differentiable on the open interval if the value of the function at the first point is equal to the value of the function at the last point. Then there exists at least one point c inside this open interval such that the derivative of the function at that point is 0. So let's look at this question. In this question, they asked us to show that the function f of x, which equals x squared minus 3x, satisfies the hypothesis of the Rolle's theorem on this closed and bounded interval 0, 3. Now, we want to check whether this function satisfies the hypothesis of the Rolle's theorem. We have stated the Rolle's theorem. Now we want to check whether certain functions satisfies the hypothesis of the Rolle's theorem. Let's see whether this function will satisfy the hypothesis of the Rolle's theorem. So, on this closed and bounded interval. Now the first thing you have to check is that check whether the function is continuous on the closed and bounded interval. What is the closed and bounded interval? 0, 3. Is this function, which is f of x equals x squared minus 3x, is it continuous here? Clearly, any number you pick from here, any number you pick from 0 to 3 and substitute for x, you will always get what? A real number. You will never get infinity or undefined. Now apart from that, this is a polynomial. We know that polynomial functions are continuous everywhere on the real line, and this is just a subset of the real numbers. Because of that, this function, which is a polynomial, must be continuous everywhere on here, on this. So it satisfies the first condition for Rolle's theorem. The function have to be what? Continuous on the closed and bounded interval. So let's make that statement. So what I have written down on the board here is just the statements I've made earlier. The function is continuous on this closed and bounded interval because it is a polynomial, and polynomials are continuous everywhere on R, on the real numbers, right? So the next thing we have to check, another criterion, we check whether it is differentiable on the open interval. Let's differentiate the function. Now, f prime of x, let's differentiate it. Differentiate x squared, what will you get? If you differentiate x squared, you get what? 2x, right? Differentiate negative 3x, you get what? Negative 3, right? Now check the derivative. Now the derivative we got, f prime of x, is a polynomial, is 2x minus 3. This is a polynomial, right? Now we want this to be continuous on the open interval. What is the open interval? 0, 3. Is this thing continuous on this open interval? Of course, this is what? A polynomial, right? So it's a polynomial. Polynomials are continuous everywhere on the real line, so it must be continuous on this open interval. And apart from that, any number you pick between 0 and 3, 0 is not inclusive because this is open interval. The endpoints are not inclusive for open intervals, but for closed interval, the endpoints are inclusive and other numbers within. But this one, the endpoints for open interval are not inclusive, but numbers within are the numbers that are included. So if you pick numbers within and substitute for x here, you will always get what? Real numbers. You will not get infinity or undefined. So this is, the function is what? Differentiable. We say it is differentiable because the derivative is what? Continuous. The derivative is what? Continuous. The derivative exists on the open interval. So I've made that statement. The function is what? Differentiable. The function we are considering is differentiable on the open interval 0, 3 since the derivative exists. The derivative exists on the open interval. I've explained what I mean by the derivative existing, because any number you pick between 0 and 3, 0 is not inclusive, 3 is not inclusive. If you substitute it for x here, you always get what? Real numbers. You will not get infinity or undefined, right? The derivative exists. So the next criterion we check whether the value of the function at the end point will be equal, right? Now, what is f at a? In our theorem, a is standing for the first point. What is the first point in this question? 0. So f at a is f at 0. So you come to your function, you substitute, replace s with 0 here. You now have 0 squared minus 3 times 0. Of course, this is 0 minus 0. And this is equal to 0, right? Now, we check for f at b. B is standing for the last point in the interval. What's the last point? 3. So f at b is same thing as f at 3. So you come to your function, substitute, replace x with 3. So you'll be having 3 squared minus 3 times 3. And this is 9 minus 9. And this is 0. So what do you notice? F at 0, that is the value of the function at the first point, 0, is equal to the value of the function at the last point, 3. Because f at 0 gave us 0 and f at 3 gave us what? 0. Both of them are the same thing, right? So this implies, let's make the comment here. This implies that f at 0 is equal to f at what? 3. So we want to get that point C that will be inside the open interval. That will be inside the open interval 0, 3. I need that point between 0 and 3. I need a number between 0 and 3 such that the derivative of the function at that point will give me what? 0. That's, I need the point C in the open interval such that the derivative of the function at C is 0. So my open interval here is this open interval 0, 3. So I need the number between 0 and 3 so that the derivative of the function at that point will give me what? 0. So what do? We come to the first place we differentiated the function and then replace x with what? C, because we need f prime at what? C. So we now have equals, so we come here, replace x with c. You'll be having 2c minus 3. You set it to be equal to what? 0. So you set f prime as c equals what? 0 and solve. And this simply means that 2c is equal to what? 3. If you move negative 3 to the right, you have that 2c equals 3. Now, you can divide the two sides by what? 2. So if you divide here by 2, you have c equals, divide here by 2 equals 3 over what? 2. And this is equal to what? 1.5. This is equals to 1.5. Now, 3 over 2 will give you 1.5. And if you check, 1.5 is a number between 0 and 3. It's a number between 0 and 3. So we were able to find that point, that number between 0 and 3, such that the derivative of the function at that point will give us 0. So we can make that statement that this implies that our C is equals to 1.5, and that 1.5 is inside 0,3. So that's bring us to the end of this session. So the hypothesis of the Rolle's theorem has been satisfied. So thank you so much for being part of this class. I'm expecting you in our upcoming class. Bye.